So it gives me pleasure to introduce my colleague Rochish Thaokar. He did his BTech from LIT Nagpur in 1995, followed by ME and PhD from IISc in 97 and 2003 respectively. This is all three degrees are in chemical engineering. So his PhD is in the area of hydrodynamic stability. He worked for some time with TRDDC in Pune, and then subsequently he did his postdoc at Max Planck Institute at Mainz in Germany in the area of polymer physics and joined our department in 2005. Rochish works in the area of droplet electrohydrodynamics for desalters, charged droplets in electrosprays, and vesicle electrohydrodynamics in electroporation applications. Well, even though I'm a chemical engineer, the sub areas in chemical engineering are quite complex. The award is for 3 of his publications on attempt to understand principles of droplet electrohydrodynamics under electric fields. His work on single droplet EHD has led to a significant increase in the activity in this area of droplet EHD in India and elsewhere. His research on droplet pair EHD has established his group to develop new designs for electrocoalescers for desalting and dehydrating crude oils in refineries. Very, very important applications for us. Both these works were proposed for the award. So I would like to invite Rochish to present his work.
So thanks Sachin for the introduction and this opportunity for presenting my work. So I'm going to talk on electrohydrodynamics of droplets, and I'll try to motivate that this area has applications in 2 very different length scales. At one end you have electro desalters, which are very important unit operations in crude oil refineries. And these are huge units. This will be around 3 meters in length. This will be around 25 meters in diameter and 25 meters in length. This is me trying to look into a desalter. This is at a fabrication workshop in Sparklet Engineers in Ambernath. They make desalters for Iran refineries. So this is one length scale where you have meters of diameter vessels. At the other end, you have lab-on-chip devices, which are hardly a centimeter or so big. And in both these 2 different diverse applications, you would see that droplet electrohydrodynamics is important. So I'm going to mostly motivate my work with respect to crude oil refining, because that's what I predominantly work in. And so the whole process here is that when oil companies drill crude oil from oil wells, it has a lot of salt and water, and it could have around 200 to 1000 ppm of salt. And when this crude oil is sent to oil refineries, like say, so the crude oil companies could be like ONGC, and this could be like a offshore platform of Bombay. And the crude oil, when it is sent to refineries like say Reliance, the crude here contains around 50 to 200 ppm of salt. And so when the refinery receives this oil and it has to process this oil in these huge refineries, the salt content has to reduce to levels of around 3 ppm of salt. And otherwise there are huge corrosion costs in the refinery. There could be poisoning of catalyst, fouling of heat exchangers and stuff like that. So there are massive maintenance costs which go into if you do not desalt the crude. So basically separate out this 150 ppm of salt in the crude. And this whole operation happens in these big vessels called desalters. So the desalters are the de facto vessels in any refinery across the world. And so it's in a way the first unit that the refinery encounters. So the operation here is critical to the downstream processing of crude oil. And so the process typically has this crude which has salt in it in the form of very fine brine droplets. And you add fresh water to this crude, around 10% of water, and you mix the crude so that all the salt in the brine is diluted by this water. and you essentially, it results in formation of a water in oil emulsion. So this is a crude oil, which has these tiny water droplets in it, and the size of these water droplets would be of the order of around 10 microns. So the settling velocity of these droplets is so small that it takes forever for them to separate out. The whole idea in the desalter is basically to for this water to separate out, so that you can have crude oil which is devoid of salt and water, and this crude oil can then be processed. So the essential role of a desalter is basically to increase the droplet size from 10 microns to around a millimeter or so that they become large, their settling velocity is large, and they can be separated out in reasonable time. So this is a small tube desalter in our lab. What you see here is crude oil, which has 10% water, and you can look at this, and it would remain like this for hours and days together. And then if you apply electric field, you would see that within a fraction of a minute, the water separates out. Okay, and this is exactly what is happening in these big desalters in refineries. So the heart of this process really is coalescence of these droplets into larger droplets so that they can settle out faster. And so towards this, we conduct a lot of experiments at lab level to understand the physics of this process. Okay. So here we have two water droplets suspended in oil, and what is really happening even in the desalter is that when you subject these droplets to electric field, the droplets come closer, and eventually they would coalesce, become larger, and this process repeats. The droplets become larger, and then they settle down. Okay. So I'm going to present to you two problems in this, which are then in a way critical to understanding of an improvement of desalters. So clearly a starting point would be to understand single droplet hydrodynamics in electric fields. And so I'm going to look at how does a single droplet behave in electric field, and then I'll look at how does a pair of droplet behave under electric field. So single droplet electrohydrodynamics, the fundamentals were established by greats in area of fluid mechanics like Professor G.I. Taylor, Torza, Vizika, Savile, and so on. And the idea here is that if you have a water droplet suspended in oil subjected to electric field, it polarizes because of migration of ions, and there are Maxwell stresses which are generated at the two poles of the droplet, such that the droplet feels electric tension because of this charge separation. Now, as the droplet elongates from the spherical shape, capillary forces come into action, and you have capillary forces that can balance the Maxwell electric stress such that the droplet can come into an elongated state of equilibrium where the electric and the capillary forces balance. So you see this droplet, it was subjected to electric field, and it takes an elongated shape where there is a balance of electric stress and capillary stress. And this elongation is expressed in terms of a Taylor deformation parameter, and it depends upon the ratio of electric stress and capillary stress. This is called as the capillary number. And Taylor derived a formula for the deformation in the linear deformation limit as 9/16 capillary number. Okay. And then there were improvements to the theory, taking into higher order corrections to the shape. And what was there in the literature when we started off this work was how does the deformation change as a function of capillary number up to a point after which it breaks. Okay, and there was not much study as to what happens to the droplet after a critical capillary number, and the critical capillary number is of the order of 0.21 or so. Okay. And so we looked at this problem by looking at capillary numbers much larger than 0.21 where the droplet breaks. And so this is a droplet put between two electrodes, and a very strong electric field is applied, and the droplet is supposed to break, and this is what happens. This is what happens when you apply the electric field. And so you see that the droplet elongates, and then it undergoes a spectacular breakup. And so clearly the breakup is much more complex than simple deformation. And my student Rahul, who did these experiments, made these observations. And we employ a numerical method called boundary integral method to understand this. The boundary integral method is essentially solving Stokes equation or electrostatics equations based on distribution of charges and dipoles at the interface, or force singularities at the interface. And the idea is that it reduces the dimensionality of the problem by 1. Okay, and so it's extremely effective, extremely accurate. And when my other student Shivraj conducted these simulations, he found that at the lobes there was a dimple present here. And so when Rahul tried to redo his experiments by having the high-speed camera at a certain angle, he could actually see dimple forming at the lobes, and then these lobes exploded. Okay, and so the reason we tried to ask here was what causes the lobes to explode, and why does the mother drop keep exploding so that eventually it leads to complete disintegration of the drop. So towards that, we calculated the total charge on the lobes, and we found that the total charge on the lobes is greater than the Rayleigh limit, which is the maximum charge a droplet can hold, which showed that the droplets can undergo further explosion. The dimple here was because of a Taylor-Safman instability, because the water droplet was pushing against a high viscosity fluid, and the instability led to formation of dimple. The droplets are Rayleigh charge limit, and therefore the lobes exploded. The mother droplet capillary number, when we calculated, we found that it is greater than the critical capillary number, and so it kept on, and the process went on going. Now, in applications, it is important to understand this process as a function of the viscosity of the two fluids, apart from the capillary number. And so an extensive study was conducted to look at effect of the viscosity ratio. The viscosity ratio is the viscosity of the inner and outer fluid. And we found that when the outer fluid is very viscous, I showed you in detail the formation of lobes and their disintegration. But when the viscosity ratio, when the inner viscosity was increased, the droplet viscosity was increased, we found droplets which had non-pointed ends, and then at very high viscosities of droplets, we had pointed ends. And these shapes led to disintegration of the droplets in various ways. I showed the charge lobe disintegration mechanism. In other cases, you have open jets and closed jets which are formed. And so overall in this work, we had a comprehensive phase diagram made for the shape deformations for a single droplet under electric field. We tried to harness this by making an electrohydrodynamic emulsifier, where we took a coarse emulsion, subjected it to electric field, and for example, in the lower video, if it plays, you see that a coarse emulsion ultimately becomes extremely fine, and we could start with a coarse emulsion and end up with a droplet distribution with average size of around 22 microns and a fairly narrow distribution. Now, so let us come to how does all of this fit into the desalter. So as I mentioned, in the desalter, we are more interested in interaction of two droplets. This is how a big desalter looks like. These are the internals of the desalters, where these are the electrodes wherein the emulsion is fed in, and the emulsion droplets get subjected to electric field and they lead to coalescence. Okay. Now, if you look at two water droplets in oil subjected to electric field, each of the droplet now gets polarized. Each of the droplet forms a dipole, and there is a dipolar attraction between these two droplets. Depending upon the orientation, you could even have repulsion between the two droplets. Now, when the two droplets come together, they would come together in a way like this. And then you can plot the separation between these two droplets as a function of time. And we compared this with boundary integral calculations as well as this analytical expression. We had a fairly good match between the two. But what is noteworthy here is that when the two droplets contact, they form a Taylor cone, and the Taylor cone is characterized by an angle beta, and this would become important in the next slide I present. So what you clearly see here is that the force which brings the two droplets close together to make them coalesce scales as E naught squared, and so it is very tempting for us to increase the electric field so that the process can be hastened. Now, when you increase the electric field, however, something else happens, and the two droplets come together, but instead of coalescing, they just touch and do not coalesce. Okay. Now, this is called as non-coalescence of droplets under electric field, and it is extremely important in desalters because when you try to apply strong electric fields, the droplets actually form chains between electrodes, and this is, so all of these things. We had discussion with Reliance Industries, who were the sponsors of the project, and they do face all of this. This is called as current surge in the desalters. And so what really happens there is chains of droplets chaining between the two electrodes, and the desalter operation has to be discontinued, which is huge loss for a continuous process like in a refinery. And so the physics of this was first given by Professor Stone's group through two publications in 2009. And what they discussed was that when two droplets contact, they form a bridge. And the bridge has two curvatures. It has a meridional curvature, which creates a negative Laplace pressure in the bridge. And it has an azimuthal curvature, which creates a positive Laplace pressure in the bridge. So if the electric field is very small, the meridional curvature is very large, and so there is a large negative pressure in the bridge, which coalesces the droplet. But if you apply strong electric fields, you see that this Taylor cone is sharp, and therefore the negative pressure because of the meridional curvature is very weak. And so there is a positive pressure here which non-coalesces the droplets. Now so this is what the status of the literature was. What we then did was conducted extensive boundary element calculations to confirm these observations. And we indeed saw that, so we actually start with two droplets, bring them closer in boundary element calculations, get the Taylor cone, put the criteria. So there's a criteria for coalescence which is around 30 degrees. And if your angle of contact is less than 30 degrees, they coalesce. If it is greater, they do not coalesce. And our calculations confirmed all of these observations. Okay. Now, in a way, the literature had stopped at that, mostly because there were issues which were not ignored by literature, especially by the, just 1 second. And so we tried to look at if the effect of brine and oil conductivity matters. Now, conventional wisdom will tell us that it should not matter because the ratio of conductivity is greater than 10 power 6. But it does matter in desalters, is what we had from the experience in the refinery. And we indeed found that the brine conductivity decreases the critical capillary number significantly. We also found that the type of oil, basically the conductivity of oil, also matters the way the two droplets contact. For example, in silicone oil, we found that there are two cones which contact, whereas in castor oil, we found a cone dimple kind of contact. And these are our boundary element calculations. Okay, so with all of this, just go to the last slide. With all of these learnings, we actually came up with, we are in process, in fact, of coming up with a lot of new designs for electrodesalters. For example, in this design, we make use of the fact that droplets can coalesce at low electric fields, but they can come close very fast at strong electric fields, although they do not coalesce. So we have a modulated electric field here, where we put very strong electric field to bring the droplets close together, but the droplets will not coalesce. And at that point, we reduce the electric field, and we construct a waveform which is then repeated. And we see significant improvement in the performance of electrocoalescer when we have modulated voltages as compared to normal electric. And so these are kind of, we've kind of patented and published this. These are the homemade desalters that we have. So I think I'll stop with this, and just wanted to, because my title had microfluidic chips also as an application. In microfluidic chips and lab-on chips, there is always this need to, to manipulate droplets, to break droplets, to coalesce droplets. And there are several designs in the literature. It's already being harnessed, I should say that. So in our lab, for example, we have this microfluidic device, and you can now see the dimension. It's pretty small. And you see that if you do not apply electric field, you could have a train of droplets which goes without any coalescence. And so these two droplets could, for example, have two different reactants in them. And then you apply electric field, and then you would see that you can make the droplets coalesce. Okay. And this is a big issue in microfluidic, where manipulating things are difficult because of the small space in the system. So yeah, so with that, these are the three publications I had proposed, and these are my acknowledgements. I would specifically like to thank Dr. Rajiv Tayal, who was with DST when the project was approved, and my students, Professor Thaokar and Nayak, who are the collaborators in my work, Anurag, Mahesh, Samir, Ganesh, and now Sachin. Thanks for being friends, and